we're going to talk about reciprocal and inverse rational functions. So let's just remember really quickly what reciprocal means. We'll talk about that in a second, but what inverse means. So when we're finding the inverse of a function, some cool things to remember is we're switching the x and y. Okay, we switch those. And when we think about what we are also doing once we switch those, we are solving for y. And we always write those either as, I'm going to put a little star there, either as y to the negative 1, or what we see them as a function notation, f of negative 1 of x. So we have to make sure we write the inverse there to notate that is an inverse. So we're going to go over some information that's important to know when we're working with rational functions. And the first thing is finding the asymptotes. So we can have a couple of different asymptotes, and we can have with rational functions, we can have multiple asymptotes depending on the function or the equation that we're given. So we're going to talk about how to find them. So to be able to find the vertical asymptote of an equation, we're going to set the denominator equal to 0. And we'll do a couple examples in just a moment. But we're trying to find out what number, what value would make our denominator 0. We know that's like an excluded value, so we have to find the vertical asymptote. We have to set that to 0. Now, once we have a vertical asymptote, the function can never cross that. It gets very close. It's almost like a magnet. It pulls it close, but it also, at the same time it gets close, it repels it, so they never touch. So it never can cross the vertical asymptote. Now, the horizontal asymptote, that's a little different story. You can have a situation where things cross it. You can have even where it swirls around them in very complex equations or functions. So to be able to find horizontal asymptotes, there's a couple of ways. Some people like to plug in a positive infinity for the x values and then solve and then see kind of where that goes to know what the value is going to be. But remember that horizontal asymptotes are actually an equation. They're a line, they're a place. So when we think about where those are, horizontal is y. So we're getting something that's y equal. So if we're thinking about a graph, if we have a line that goes across here, maybe that's y equals 3. Okay. When we have a vertical, that's always as x equals, because we're solving for the denominator. X is whatever in our denominator, so we know that one is going up and down vertically. We can't cross this one. This one's never crossed. Okay, so make yourself a few little notes for understanding. So some people like to plug in the positive infinity. I'm not one to do that because then there's more room for kind of lack of understanding. Plus sometimes it takes a little longer, but it's a great strategy. Others are just using the rules. So we're going to use the rules, and I used N for numerator and D for degree. They will use P and Q. A lot of times you'll see this rule and they'll use P as the numerator and then Q as the denominator. As a rational function. So notice here it says if we have a degree of n, so a degree on top, and we're talking about whole degree of the equation, whatever the expression is, and it's greater than the degree of the denominator, we will actually have none or no horizontal asymptote. Okay, there will not be one. If the degree of the numerator is less than the degree of the denominator. So think about the bottom of the equation being heavier. It's kind of holding it down. That is always going to be y equals 0. Okay, so that one's a good one to always know. If they are equal, then we have to set up a ratio. So if they are equal, we're going to set up a ratio where y would equal the leading coefficient over the leading coefficient. And again, we'll do an example of these in a moment. And then that will give us our equation of where y would be. Okay. Now, when we have no horizontal asymptote, when we had the first case here, we then need to look to see if we could have a possible slant asymptote. So if we're in this situation, we need to look to see if this rule would apply. So a slant asymptote is when the degree of the numerator, so the n, the top, is just one more than the degree of the denominator. Okay, and we find that slant asymptote by then using division to find what our new function will be, but we ignore the remainder. Okay, so let's do a couple examples here. So we're going to use our rules here. These are some rational functions. I am not going to factor them for this rule situation, just so you can see it doesn't matter if they're factored. If they're factored, same difference. So we're going to look at our degree here. So we look here and we see a degree right there. There's no number, so we know that's a degree of 1. And down here, our degree of this is 2. Okay, so we have the numerator is 1 and the denominator is 2. So when we look up here, we know that the numerator is less than the degree of the denominator, so we're going to have an equation for our horizontal asymptote that is y equals 0. So if we were making a horizontal asymptote here, then it would actually go right through y equals 0, right across our x-axis. Okay, now let's look at the next one. Make our a little bit smaller here. So we have a 2 here and we have a 2 here. So they are even. So we look up here, the degree of n and the degree of d is even, equal to each other. We set them as a ratio. So our leading coefficient, which would be here, 2 over our leading coefficient of the bottom, which is 3. So then our equation is y equals 2/3. So then on a graph, at 2/3, maybe 1's right here. 2/3 of that, maybe right there. No, eyeballing it. We would have a horizontal asymptote, and we do that with a dotted line. Okay. All right, let's look at our next one. We have a degree of 3 and a degree of 2. So when our numerator is larger than our degree of our denominator, which is the case here, we have no horizontal asymptote, but we need to check for a slant. And the slant only happens when the numerator is 1 more than the degree of the denominator. Well, 3 is 1 more than 2, so this could be a slant asymptote, so we're going to go ahead and do some division. Now, when you use long division, and you can use synthetic if you could. I can't use synthetic here because this is a division of something square. We can only use that with linear. So we're going to set up our long division. So we have x squared, our placeholder 0x minus 1, all divided into x cubed plus 0x squared plus 0x plus 27. Then we're going to follow our process. So I think, oh, x squared times what gets me x to the third, or x third divided by x squared is just x. Then I'm going to multiply. I get x to the third, 0x squared, and a negative 1x. I then have to subtract. So I'm going to change my sign. Subtract. Doesn't really matter about this one. We'll do it either way, and then change. So this would cancel out, and then I would have here a 1x, and then bring down my 27. Now, when I go from here, and I start saying what x squared into 1x, I know I'm going to get some remainder, and I'm getting a remainder because I've got this last number brought down. So I don't have to worry about my remainder in this. I can ignore it. I just need to know like the main equation, like if it's got a slope or y-intercept. This one is just going to be y equals x because the remainder is ignored. So then I know that my slant would actually be right through where y equals x, which is usually our reflection line. Okay? All right, we're going to talk about a reciprocal and what that is, and then how to find the horizontal asymptote and the vertical asymptote, as well as a domain and range for the reciprocal. All right, so the reciprocal parent function is f of x equals 1 over x. Now, with the reciprocal, its inverse is its own, and this will make sense in just a minute. So you'll see kind of how it works. Remember that inverse always reflect across y equals x, no matter what type of function we're talking about. And we're going to talk about this graph. So we'll start out with thinking about the vertical asymptote. And so we know that we're going to set the denominator equal to 0. Well, the only thing we have in the denominator on this one is x. So x equals 0, obviously x is 0. So our vertical asymptote is x equals 0. And then I'm just going to plot that on my graph. So when x equals 0, it's literally just going right through the y-axis. So that's my vertical. That means my function is never going to cross over that. Okay. Now let's find my horizontal asymptote. So we're going to look at our degrees. So we'll look at our rules here. So if we look at the top, we have just a number. And numbers don't have degrees. So that's a 0 degree. So we'd have a 0 up at the top and a 1 on the bottom, because that's a degree of 1. So when we look at here, this is bottom heavy again. So this is always y equals 0. So we're going to go ahead and plot that one as well. So y equals 0 right through here. Okay. Now, before we can tell what type of domain or range or type of graphs, we got to have a graph on here. So a lot of times people are like, they just memorize what the parent function looks like, and of course I know, but if we don't know what it looks like and we need to graph it, we can just pick some points. We know that we're going to pick on either side of this vertical asymptote, so we could put in 1 and see what we get. So if we put in 1 for an x, 1 divided by 1 is 1. So we know that we would actually have a point at 1, 1. Okay. If we put in, say, a 2 for x, we would have 1/2. So 2 is up at a half. Okay, not 1/2, but a half. So we'd have a point here. Okay, so that tells me, because I have a horizontal asymptote and a vertical asymptote, I'm going to have a function that gets close to those lines and my end behavior up and then to infinity. And then because I have a reciprocal and this is a rational function, I'm going to have something on the other side because they have to go kind of give both their parts. When we think about negative numbers. So if I put in a -1, what I would have, I know I'd have a -1. So I'm going to roughly have another piece of my graph. And this is the whole reciprocal parent function graph, what it looks like. Okay, this is not its inverse. This is the whole parent function reciprocal graph of a rational. So this actually has a name, this graph, and it's called, do not confuse that with the term that we use in English. Okay, so now we're going to talk about our domain and our range. So when we look at our domains, we're thinking about our x's, and when we're thinking about our x's, we can, let me use a different color here. We think about, well, we can go here, we can go all the way here, but boom, when we hit this wall, we are not going across it. So we cannot include 0. But as soon as we start on the other side, there's some x values, and they go on forever. So the only thing that's excluded here is the 0. So we can actually write this as x such that x does not include 0. Okay, so it has all real numbers except for 0 in our situation here. Now, we can also write that in different notation, which we'll do some examples, and you'll see that in other notation. Now, with our range, we always start from the bottom, and we're looking from going from the bottom to the top. So if we think about here, we've got negative infinity, and we go all the way up, and then we have a horizontal asymptote right here. That's not included, okay? We stop there. It's not crossing it. But then on the other side of it, it picks up here and continues to go, okay? So we can write that as everything except for 0. So we can write it as y, such that y is not 0. So this particular one is pretty self-explanatory and easy to do. They're not always like that, but this one is your reciprocal parent function. All right, we're going to talk a little bit now about the standard form of a reciprocal function and what happens to it when we shift it around. As we've talked about previously in all of our different functions, we can do things to our standard form of that function and move it around. Left, right, up, down, reflect, stretch, or compress it. So this is our standard form of a reciprocal function. You can see that we still have the H and K showing up in there, and we still have the A showing up in there. And they have different kind of jobs, just like they do in other things, of what they make things move, how they make them work. So when we look here, the H is got to deal with the horizontal shift. So we think about what is here. This moves things left and right. Remember, if we put a positive in there, when it looks positive, I had something like it was, 3 over x plus 2. This looks positive. We actually put in a negative. So think about what it does. Shifts left, shift right. Same rules as before. The K on the end, attached to it out here, actually does the vertical, the up and down, just like it does in the other functions. The A being negative still handles the reflection over the x-axis. So that's important to remember. If the A is bigger than 1, it represents a vertical stretch. And then if it is less, it is a compression. But of course, can't be 0, so it is a compression. So when we look at something in this form, we could quickly determine that the vertical asymptote is whatever the H is. So x equals H, because we write that as an equation. And the horizontal asymptote is whatever the K is, so y equals the K. So that's just a quick overview and reminder to kind of help you how things work as far as transformations. This is just its form. Now, a rational function comes in this form. F of x is equal to P of x, so some type of expression over Q of x. And basically, P of x and Q of x are polynomials. Okay, so what we've just talked about in our prior unit are polynomials. And Q of x, which is our denominator, cannot equal 0. Okay, we can't divide by 0, we get an error. So we can't have anything that we could put in the denominator that would make it a 0, and that's where exclusions or restrictions come from with rational functions. So we're going to talk about how to look at them and kind of sketch, find some vertical and horizontal asymptotes, find the domain and range, and we're going to talk about the inverse and sketch just the original. We're not going to sketch the inverse, but we're going to just sketch the original and talk about the domain and range. So you'll start seeing, hopefully, how these connect with everything we've done already before. Our first example here is 1 over x minus 5. So we're going to first find our vertical asymptote. We set the denominator equal to 0. So if I set that equal to 0, I would see that x would be 5. So my vertical asymptote is x equals 5. Easy breezy. Now I can use my rules. Think about my degrees. My degree of my top numerator is 0 because it's just a constant up there. And then my denominator is 1. So then that tells me, based on the rules, in this case, y is 0. So I'm going to go ahead and put my vertical and horizontal asymptote. My horizontal asymptote goes y through 0. And then we'll do another one, x is 5. Now remember, it cannot go through the vertical. So I can have my function, I could have it maybe here and here, well, maybe, or I could have it here and here. So this is the part where people are not sure where to put it. Well, you kind of learn by doing a lot of these at first, but if you look to what is happening here, if I would pick a number, let's say the number 6, because I know I can't cross this line here. And so if I go onto the other side, I'm either going to be down here or I'm going to be up here. Once I know one of them, I'm going to know the opposite because this is a reciprocal type situation with the functions. So I can plug in 6. If I plug in 6 for x, 6 minus 5, and 1 on top. 6 minus 5 is 1. 1 divided by 1 is 1. So I know it's going to be 6 and 1. Okay, I only need 1 point. Now I know immediately this is going to go in some fashion here. I don't have exact points. I'm just sketching. So because this has to cross across y equals x, and this has been shifted, because if we look here, this -5 is the h that happens. And notice it's been shifted 5 to the right. So if I shifted it back, it's just our reciprocal function without the -5. So I would immediately know the other side goes here. Okay, so this is this function, and now we can write the domains for this function. So in this one, I'm going to write the different notation that we've used in the past. So we think about our domains or our x's. Well, we've got -infinity over here. It goes all the way till it hits 5. It can't go past 5, and 5 is not included. So I can actually write it -infinity with my parentheses to 5, open parentheses, union, and then it starts up again. So on the other side of 5, it goes to positive infinity. Well, we've got to count for 5, but it's not included, so that's why we use a parentheses, and then to the positive infinity. Okay? And then with our range, we look here. We start at our -infinity. We go up to our horizontal asymptote, and it can't be included. Okay? We have to stop there, and then we start back over here and go up. So in this one, we're going to go -infinity to 0, union, 0 to positive infinity. And if you remember from doing inverse, when we have domain and range, they just switch spots for our inverse. So that means we know that our domain in our original is now our range in our inverse, and then vice versa. So we know that our domain for our inverse is going to be in -infinity to 0, union, 0, positive infinity. And then our range for our inverse will be our domains from the original. So it's -infinity to 5, and union with 5 to positive infinity. All right, so now let's find the inverse. Remember, to find the inverse, we switch the x and y. So I'm just changing my f of x to y. Now we're going to switch them. X equals 1 over y minus 5, and we're going to solve for y. Well, I have a fraction on the bottom, so I'm going to multiply by that fraction to both sides. And I end up with these canceling out, and I get y minus 5, x there equals 1. Now, I want the y by itself, so I'm not even going to factor this out. Or distribute this out. I'm going to just go ahead and divide by x. These cancel out. I'm left with y minus 5 equals 1 over x. And then I'm going to add 5 to both sides. So I end up with f of -1 of x is equal to 1 over x plus 5. So if I think about what's happening, if I were to graph my reciprocal, and I want you to put these in Desmos and see kind of how it looked originally, and then your inverse, you should see kind of how it's changed, and then it's crossing the y equals x axis. All right, I want you to try number 2 and number 3. Find the vertical and horizontal asymptotes, domain and range, find the inverse, and then go ahead and sketch the original and see how good you do, and then check yourself. All right, so if you'll look at 2, we had a vertical asymptote of x equals 4, setting the denominator equal to 0. And then we had a horizontal asymptote as y equals 1. The degrees were the same, so it's just a ratio of 1 over 1. And then we graphed them. Now, I wrote these domain and range is the other way, just excluding the one value they could not be. So basically, we're saying they're all real numbers except this number. And it's a little bit less time consuming. I'm fine with either way, but you need to know what both mean. And then we found our inverse of this function. Now, I put a little note here on number 3, how to know which way to sketch. Remember, plug in. If you're not sure which way to go, plug in. So a lot of times that can be a little bit confusing because we think, well, maybe it's because there's a negative. That's why we do opposite. It has to do with the whole function itself, the whole equation, and how the operations end up being. So be careful, plug it in if you're not sure. It's just a quick little thing. And when we start graphing, you're going to have to plug them in anyway. So get used to doing that. So this would be number 3. Now, let's look at number 4. Number 4, we already have and kind of understand what is going on here. So we already know that the vertical asymptote is going to be where we set the denominator equal to 0. This one's pretty easy. We also can look and see there's no h down here. There's no other number connected to x. So that tells us it's going to be 0. There's nothing there. And then this is our k spot here. So that tells us y is -2. So instead of doing a whole lot of work and looking at the degrees and all that good stuff, we could just look that way. Now, if you were looking at the degree rule, we'd have to look a little closer, because if we just looked at this piece here and we looked at the degrees, we have a 0 over 1. And you may think, oh, okay, well, that's bottom heavy, that would be y equals 0. Well, if it was just that, it would be. So this degree, this would make it 0, but then we have a -2. So together, this is y equals just the -2. That's another way to think about it. You can still use those rules, or you can recognize that k is the horizontal asymptote. So when you found your inverse, hopefully you did that correctly with your algebra, and then you graphed and found your domain and your inverse domain and range as well. Okay. All right, we're going to look at number 5 and number 6. Now, number 5 is not a toughie. It's the same kind of deal. We can kind of look at this. I just want to look at it a little bit different. So when we think about this one, if we're looking for our vertical asymptote, we can, yes, set this bottom equal to 0. That's what we're doing. So we know this would be x is -3. We can also look at this h value and what do we put in there to make it work, which would be -3. Now, with our horizontal asymptote, we know it's normally a k. Well, k is not there. Okay, so in this case, we might think, oh, it's just 0. But we needed to make sure that our degree rule works, because if it's something else over here and we're adding to it, we have to think about that. So when we look here, this is a 0 degree and a 1 degree. Okay, well, that's usually y equals 0, and we're not adding anything, so it's going to stay y equals 0. Okay, all right, and then you would go ahead and find your asymptotes and go ahead and plot them, and then go ahead and graph. So take a moment to do that for number 5, and then check to see how you did. All right, and then here's number 5. We've got it graphed. Notice that our vertical asymptote, we never cross it. And for these, we haven't crossed a horizontal asymptote. Those are really kind of odd looking creatures, and we'll see those later, but we haven't crossed them as well. This kind of are our barriers to help us stay in track when we graph that we'll be going into soon. So here are our domain, our ranges. Again, I wrote them the shortcut way, and then hopefully you have your inverse. So we're going to go into number 6, and we're going to look at it. Let me come up here to number 6 that's not written on, and we're going to look at it by itself, and let's think about what we know. So this one is a little different because we have a quadratic on top in our numerator and then a linear on bottom. And so when we first think about our vertical asymptote, we set it equal to 0. So if we set this equal to 0, we would get x equals 1. So great, easy, we can do that. Hopefully that's pretty self-explanatory. Now we've got to look at our horizontal asymptote. Well, horizontal asymptote, we normally have a k out here, but we don't have anything sitting out there, but we can't just assume it's y equals 0 because we have some different things in our numerator and denominator. So we have a degree of 2 and a degree of 1. So 2 over 1. When the top degree is larger than the bottom, we have no horizontal asymptote. So we have no horizontal asymptote, but we need to check for a slant. So a slant, so I'll mark this out and I'll put a slant there. We need to check for that to see if we have one. So a slant was only when our numerator is 1 more than our denominator. Well, in this case, it is. So then we're going to use division to find it. Now, because this is a linear, we can actually use synthetic division, and we know x would be 1, so we're going to use 1 in our box. And then we have to account for each piece. So we have a 1, a -2, and a -3. Follow your synthetic division, and you end up with quick here. -1, -4. The last piece would be our remainder. We ignore our remainder. It's not important. So we start off with x squared, so we know this is going to be x, and then minus 1. So that is actually our horizontal, our slant asymptote. So we write that as y equals x minus 1. So let's go ahead and graph those first. So we'll do our vertical one. That's pretty straightforward. Our vertical one, right, is x equals 1. And then our slant is going to actually be that, a slant. So we have y equals x. So think about your slope. Your slope is 1, and your y-intercept is -1. So we're going to start at -1, and we're basically going up by a slope of 1. So I'm going to go all the way to the end there. It's not very straight there. And we'll come down through here. All right. So now notice that we have a two asymptotes, a vertical and a horizontal, and we got to decide where we're going to graph at. Now, we kind of have some options. We're either doing here and here, or we're doing here and here. So the way for us to know that is to pick a point and plug it in. So I'd like to go really close to my vertical asymptote. So I'm going to pick 2, since our vertical is on 1. I'm going to pick 2, and I'm going to plug it in. And now when you plug it in, you don't have to really get the numbers. And this is something that is just a strategy that's easy to use. So we're going to plug in a +2. So +2. And we're going to think about what we're plugging in. So I'm just going to rewrite here what our problem was, and then show you that way. And then after that, you don't really have to rewrite this. So when I plug in a +2 here, I'm going to get out a positive. And I plug in a +2 here. A positive times a negative gets me a negative. Okay, so I'm going to be doing minus. And then -3. So a plus minus something. So I think about what's happening here. I know that I got a 4. Minus a 4, those went away, and I'm left with a -3. So I'm left with a negative, okay? And I'm going to put -3 for now, but I'm just left with a negative on top. And here, when I put in a +2, so a positive number here, a positive and a negative, because that positive is bigger, I'm going to end up with a positive, in this case, a +1. Which gives me a 3. If I didn't know these numbers, I know that a negative divided by a positive is a negative. So when I go here, I put in a 2, I'm actually going this direction. I'm going negatively. So that immediately tells me that I'm going to be going this way, and I have to go this way because I can't cross over that horizontal asymptote in this case. Okay. So as soon as I know that, I also know this. Okay. Now you could have picked a very easy one to try first. You could have picked 0, which would be your one of your intercepts. So I could have put 0 in. Obviously, I know if I put 0 here, that's gone, that's gone. I'm left with just a -3. And if I put a 0 here, I got a -1. Well, my signs are what's really helping me kind of know. A negative divided by a negative is a positive. So I know that if I put in a 0, my function has to behave that direction, which means to follow my asymptotes, it's going to be on either side. So we'll get some more practice with this. For our domains, I'm going to write them long way this time. So our domain, if we think about our domain, what's happening, we have -infinity, we go all the way over, we hit right here, and we can't go any further. So right to 1. We hit. So we're going to write it as -infinity to 1, not included, union, and then on the other side we pick up again, and we then go forever with values of x. So we're going to have 1 to +infinity. Now with our ranges, if we start here at the bottom with our range, we're going up, 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 up. Notice right here though, when we hit here, if we look over, we have some things happening there. So this is not excluded. We actually have some values that are going at the same place where y equals x minus 1 or y equals x. Okay, so these are actually all real numbers. So this is, you could say y and use the little weird little symbol, all real numbers here. All right, so if we look at the inverse, we know that they just switch spots. So for our domain, we'll say all real numbers. We can just write it that way as well. And then our range, I wrote is the other way, y such that y is not equal to 1. Now, when we think about looking at this as an inverse, if you try to set this up to try to find its inverse, you would have a hard time because this is actually going to have more than one inverse. And the reason is because of something called a one-to-one relationship. This is not a one-to-one. And a one-to-one is checked by a horizontal line test. So remember, when we learned about a horizontal line test, we said in our original function, if we could go across and it was a function, then we knew it was a one-to-one, and our inverse would also be a function. But if we notice here, we're hitting here and we're hitting here at the same exact time, so it is not a function because this is not a one-to-one. So you would actually have kind of a crazy looking graph if you try to do an inverse with this, because you're going to have two separate answers, so it's going to end up making a crazy picture. So for this one, we're not going to find the inverse because it is not a one-to-one, and I'm going to put a note here just to remember the horizontal line test. Okay, this is not a one-to-one function, so therefore its inverse does not have an inverse. It has two actual inverses, not just one.